So in the exercise, we asked you to consider a problem where Amoeba Manufacturing was going to manufacture a certain number of boards, and they had two options. They weren't sure if they were going to need 100,000 boards or 200,000 boards. And so they could either manufacture all 200,000 boards now and see what happened, basically potentially take a loss if they didn't use those second 100,000 boards, or they can manufacture 100,000 now and then wait and see and manufacture another 100,000 later. So you should have drawn something like what I've shown now. And I'm going to talk through this so you can see how it works. So we've got two options. The first option is to manufacture 100,000 boards now. That's going to cost us $450K, which is the $200,000 cost of manufacturing the boards, plus the $250,000 fixed cost of manufacturing. And we're going to get $500K from that right now. And then we can see if we get the next order. If we don't get another order, then there's zero additional cost or revenue, and our net profit is $50,000. That's the second path down. If there is a further order of 100K, then that's going to cost us another $450K to manufacture them, which is the fixed cost plus the cost per board, and we get a further $500K, and our net profit is $100,000. So if we go down that route, we can calculate our expected value, which is 100K times 0.5 plus 50K times 0.5, which is $75,000. The other option we can take is the bottom half of this diagram, which is to manufacture all 200,000 boards straight away and take a chance. So that's going to cost us $650K, which is the $250K fixed manufacturing cost plus the $2 per board, which is $400K, making $650K in total. And we're going to get $500,000 in immediate revenue. And then either we get another order, in which case no additional cost, but an additional revenue of $500K, making a net profit of $350K, or we don't get the additional order, in which case no cost, but also no revenue, leading to a net loss of $150K. And the expected value for that is $350K times 0.5 plus minus $150K times 0.5, giving us an expected value of $100K. So despite the fact that it might seem more risky to manufacture all 200,000 boards, actually the expected value is higher, and that is our preferred option. Now, you might conclude quite reasonably that you don't actually want to lose $150,000 potentially, and that would be a perfectly reasonable decision to make. Just bear in mind that you're then not making the decision based on expected profit. You're making the decision based on not wanting to lose $150,000. And it's important to separate out those two things. And going through this exercise lets you separate out the different considerations that you're applying, so that you can say, well, listen, the expected value of this decision is lower, but it doesn't expose us to this risk of potentially losing a bunch of money. And so that lets you refine your scenarios and make better decisions by being explicit about what you're considering. The other thing that you can do, which I think is really cool with decision trees, is calculate the value of information. So this is a course in the School of Information, so it's important to think about the value of information. And information can have value in several different ways. First of all, information can reduce uncertainty about decisions that have economic consequences. Information can also affect the behavior of other people. If we spread information, that can change people's behavior, and that can have economic consequences. It can move the stock market, for example. And then finally, information sometimes has its own market value. People will actually pay for information. We're going to look at the first of these ways in which information can have value by reducing uncertainty about our decisions. So, as I said, often you don't have a lot of precision in the numbers that you allocate to the value that something will provide. And when you have not very much precision, when there's a wide range of possible outcomes, one thing you can do is perform a measurement by running an experiment, for example. And so Doug Hubbard has this nice definition of measurement, which I think is quite thought-provoking. He describes a measurement as a quantitatively expressed reduction of uncertainty based on one or more observations. So when you measure something, you reduce your uncertainty based on observations, and that's what we do when we measure things in science, and also when we run experiments. We're trying to learn more and become more precise and reduce uncertainty. We can actually use decision trees to calculate the value of information in this sense. What we could do is remove the very top path where we make 100k, but then there's another order for 100k. That would be avoided if we knew the answer and it was 100k. Equally, if we paid for that information and the answer was that 200k would be our order size, we could remove the bottommost branch of this model where we pay for 200k, but we only get an order for 150k. And so by taking this decision tree and removing the branches where we make a decision and then that decision turns out to be wrong, we can model what would happen if we had perfect information. And so if we do that, the decision tree looks like this. There's a 50% chance that we will get an order for 200,000, in which case our net profit is 350k, and there's a 50% chance that we will get an order for 100k, in which case our net profit will be $50,000, and we can work out the expected value of this scenario in the same way. We multiply 350k by 0.5, and then we add the result of multiplying 50k by 0.5, and the expected value of this scenario with perfect information where we don't make a choice that turns out to be wrong is 200k. So what we can then do is calculate the value of perfect information by looking at the decision tree where we have perfect information and so we don't make a choice that is unsuccessful, and then compare that to our best expected value in the previous decision tree, which was 100k. And if we subtract that from our expected value in the perfect information decision tree here, you can see that the result is $100,000. So that places an upper bound on the amount we should pay for perfect information. Using decision trees, we can actually calculate what perfect information is worth. People often ask, well, how much of an MVP should I do? How much should I spend on my MVP? Well, we can actually work that out using decision trees and place an upper bound on the amount of money you should spend to get information about a decision by, for example, running an experiment. So, interesting stuff, I think. Now, there are some problems with decision trees. Firstly, humans are risk averse when the stakes are high. That's why intuitively you might have thought in that Amoeba manufacturing case that the 200,000 upfront manufacturing run would be a risky decision. Humans are risk averse. There are a couple of things that you can do about that. Firstly, decision theory has this concept of utility functions, which allows us to actually quantitatively model that risk aversion. That's in the decision tree primer, that is in the reading list. So if you're interested in finding out how you model that, that's in the primer. The other thing you can do is reduce the stakes. Douglas Hubbard, in his book, How to Measure Anything, which I've referred to already a few times in this unit, says when a risk-averse person takes a large number of very small bets, their choices will be close to risk neutral. So just avoid taking big bets. Take a large number of smaller bets, and then you can avoid risk aversion. And this is what we mean in product management when we talk about not doing huge projects and programs, and instead breaking things up into small batches, building prototypes, building or running MVPs, gathering information and proceeding in small increments. It's actually much better to do that. As we spoke about in the previous unit, organizations often don't like doing that because they're running in this kind of project-based mindset where you have an annual budgeting cycle and you have to take big bets. You want to avoid that as a product manager as far as possible. Find a way to split it up into smaller chunks and make smaller bets, because you'll avoid risk aversion, you'll get faster feedback, and you'll be able to course correct more quickly. Also, these decisions are not normally binary. Often there's a continuum of possible options. You could use calculus to model this. A very popular way to model a number of different scenarios is using Monte Carlo analysis, where you create probability distributions for the inputs to your model and then just basically create a bunch of numbers that fit into that probability distribution and run the model many times with those different inputs that match the distribution, and see what the distribution in outputs from your model looks like. So that's a very commonly used technique. So you do it with spreadsheets. There's examples in Doug Hubbard's book on how to do Monte Carlo analysis. That's very common as well when you're doing modeling. However, there is one final problem with decision trees that we can't solve within the context of that model, which is that they don't capture time dependence. So every decision you make in product management will be time dependent. Something that may look like a good idea now, 6 months or even 3 months or 2 months down the line may not be a good idea. And this is not captured in decision trees. So we need to find another model that we can use to think about time dependence and how we capture that. And that's what we're going to do in the next module, where we look at cost of delay.